Alright, now we're going to go in section 6 of chapter 10, plane curves and parametric equations. This is going to be a little different. We're going to be looking at curves in a slightly different manner than the way we have done in the past when we were dealing with x's and y's or even r's and thetas. And I always like to use it as an example. Let's say that on a surface, on a table, we have a fly and a spider that are crawling along the surface of this table. And they crawl in such a manner that their paths do cross. As you can see here, I've got the red one here, or the pink one here is the spider, and the green one here is the fly. And I've set this up on the set of axes so you can see that they intersect, their paths intersect at 0, 2. Now, does that mean that the spider catches the fly? Does that mean that the spider and the fly pass 0, 2 at different times and the fly escapes? So we won't really know if the spider gets the fly or not. It says, does the spider get the fly? Well, it's kind of based on the timing. People's paths cross all the time, but that doesn't mean that they meet one another. And that might be what's happening here with the spider and the fly. So we need to bring in a third concept besides, the x and y coordinates, but the time that they're at a particular point along their lines of travel. So this third variable, which we refer to as a parameter, and we normally use the parameter t, because t in most cases represents time, is going to be used to define x and y to determine if indeed the spider catches the fly. So here's a definition. Plane curves and parametric equations. Let f and g be functions of t over an interval I. Then the set of points defined by, notice here, x, y defined by f of t and g of t, so we're defining the x and the y in terms of this parameter t, is called a plane curve. The equation x equals f of t and y equals g of t are called parametric equations of the curve, and t is called the parameter. Alright, now to graph a plane curve that uses parametric equations, what we do is we set up a double t chart. Now a double t chart means that we're going to have a value for t, and then we're going to use that value to compute values for x and y. We'll plot those points and we'll be basing this on increasing values of t. Give it orientation. We use the arrows to show that the orientation of the plane curve, how it's going. Is it going from right to, like if, for example, is the fly crawling this way or is the fly crawling this way? It'll give us an idea. So we have an example over here that I've set up where I have two parametric equations, and we're going to base this on the limitations here that t has to be between -4 and 4 inclusive. So we're going to sketch the plane curve defined by the parametric equations, x equals the absolute value of t minus 2, and y equals t over 2. And we're going to do this, like I said, over the interval from -4 to 4 inclusive. So what I'm going to do, and I left some space here, is I'm going to create a double t chart. So I'm going to have t, and I'm going to have x, and I'm going to have y. So I'm going to pick values. Now to make life easier for myself, t could be any number in there. I'm just going to use the integers. So I'm going to go -4, -3, -2, -1, 0, 1, 2, 3, and 4. And then I'm going to plug these numbers in one at a time into x, the parametric equation x equals the absolute value of t minus 2, and the parametric equation y equals t over 2. I might get some fractions, but I can deal with it. So if I plug in -4 into here, the absolute value of -4 is 4 minus 2 is 2. If I plug in -4 here, -4 divided by 2 is -2. So there is a point right off the bat. I have 2, -2, I have 2, -2. That's this point right here. This is where everything is starting. Okay? Then I plug in -3. This is going to give me 1. This is going to give me 3 halves. So I'm going to have, actually, -3 halves. So this is going to give me 1, and -3 halves would be about here. And then I'm going to plug in -2, so that's going to give me the absolute value of -2 minus 2 is 0, and -1. That is not very well drawn. I think my first one's off a little bit here. Actually, I think this one's off a little bit as well. That's what happens when you try to graph from the wrong angle here. Okay. Now I'm going from this point to this point to this point. -1 now would give me a -1 and gives me -1/2. negative 1, negative 1/2. Let's see if I can do a better job with this one. Then if I plug in 0, I get negative 2 and I get 0. That's easy enough. If I plug in 1, absolute value of 1 is 1 minus 2 is negative 1, and I get 1/2. So I have negative 1, 1/2, excuse me, something, negative 1, yeah, 1/2, I'm sorry. Haven't done one of these in a while. Plug in the 2, I get 0 and 1. Plug in the 3, I get 1 and 3/2. And then plug in the 4, and I get 2, 2. So what's going on here, hopefully you can see this, is that I have kind of a V shape here, not a greatly drawn one here because of the way I plotted these points, but hopefully not only can you see the path, and of course it would help if I could get these points to match up, but I also have the following orientation. So I put the arrows here to indicate the direction in which it's moving. So if that was for some reason a fly crawling along a surface, he'd be going this way. Maybe he spots the spider down the way and he cuts back and he goes this way. And you can see not only the curve, but you can see with respect to the parameter t, the position at each one. Now, I have seen some students write where this is t equals negative 4, this is t equals negative 3, this is t equals negative 2. So you can also see the exact location and at the exact time. Now, I don't know if I would necessarily have you do that, but that way you can at least get an idea of where the object is with respect to time. And now we just need to do some more examples. That's not going to be near enough.